Welcome everybody for this MIDAS training series on steel composite Girder bridge. This webinar is also going to emphasize on the use of IRC 22 code for steel composite. I'll just have a quick overall view of what all things are going to be covered in this webinar. So the contents, introduction, bridge overview and description, like what type of bridge we are going to attempting to model, and then simple modeling techniques that would be helpful for you to quickly model the bridge, and then analysis and result interpretation, followed by the design procedure that has to be adopted for composite steel design as per IRC 22. And then detailed, we'll also have an overview on the detailed calculation report that is generated by MIDAS in accordance to the code, and then some few live projects applications, as in like how to model certain components in MIDAS, and then used in live projects, and then finally a summary and a conclusion of what has been dealt with. So I'll just proceed further. So just a brief introduction about the software. So you can just see MIDAS could almost cover any type of bridge that even exists. So starting from a simple slab bridge, truss bridge, PSC bridge, integral abutment to consider the soil interaction, moving mobile scaffolding bridge. So any type of bridge, it can handle dynamic analysis, static analysis, non-linear, linear. Mostly what are things that are in practice, most of these things could be comfortably handled by MIDAS Civil. So in this case, in this webinar, as I've told, we are going to concentrate on steel plate girder bridge. So the key features of MIDAS, it is a one-stop solution. It is not only going to help you model, analyze and get the results, it will also have potential to design the members and also gives a excellent Excel report which could be later used. So generally it is an iterative process. You get the design and then make some modifications, and then so it keeps going on. So all these repetitive work could be tremendously reduced by using MIDAS Civil. So this webinar, this is what we are going to show you, like all of these process we are going to handle and help you out understand how MIDAS helps you better in all of these processes. So first overview of the bridge. So this bridge is a straight bridge, and we are going to try to model a straight bridge which is of it's a two-span bridge with 24 meters and 28 meters span length, and then the roadway width is 10 meters, and the spacing of the cross beams, we are considering 8 meter and 7 meter. So this is just an overview of the cross section of the bridge. So it has 4 girders, and you can also see the bracing arrangements. We have a X bracing, and it is a plate girder composite bridge, by the way, and it has a X bracing and a K bracing also. So before we get into modeling, I'll just quickly explain what type of elements or bridges we can model using MIDAS. So if you look at these options over here, you can model a steel I bridge, steel box bridge, steel tub bridge, and then apart from this, the type of elements, like you can have all of them as a frame element, that is a 1D element, line element. Then you can also have them as a plate element. Not only this, we can have combinations as well, like if you're interested in having the slab as a plate and girder as a frame, that is possible. We have some special options like resultant forces, which will give you resultant of the beam and the plates acting together, and also all of them as plates as well. So you can also have tapered sections, and yeah. So this is again overview of the type of model. So first thing is the all frame, and next one is the all plate model, and then is a deck as plate and girder as frame model. So in MIDAS, interestingly, we have a wizard that will help you quickly generate all of this just by inputting the basic parameters that is required. So just one more depiction of the type of elements and sections you can define in MIDAS. Apart from straight bridges, we also have inputs for generating a curved bridge with an ease. If you can just see, just with inputs as span length and radius, these curves could be beautifully generated without any hardship. It could be a single curve of same radius, transition curves, whatnot. You can do all type of complex curve modeling using this wizard. After this, I'll just show you a demo using the software itself, how this wizard would help us to quickly generate the bridge without taking any time. I'll just cover the basic definitions that we'll have to give before we proceed further. So the first thing is the material properties. So wizard, before using the wizard, we'll have to define all these in the base model. So that is the material properties. Again, if you see in material property, we have again a database, a vast database depending upon the codes, which will help you quickly select all those compressive strengths. And then we also have options to give user defined materials. This basically comes into picture when we are interested in modeling dummy elements. And then defining the section, again we have dedicated section tab which allows you to define different types of sections. So in this case, if you see, we have steel composite section type which allows you to define the slab and girder separately, and also allows you to define the modular ratio to be considered for the calculation purpose. And then defining the sections, talking about the sections, we have again a set of database depending upon the steel properties, section properties that is available with the codes. Apart from that, if we have any built up sections or user defined sections, again we have options like AutoCAD input, GSD, that is general section designer, or section property calculator, which will help you easily model these built up sections and help you quickly import it with MIDAS, thereby reflecting the actual behavior of the properties without have to compromise on anything else. This is also going to give you a graphical view of how these sections are, and also will give you accurate results and behavior of these sections being used. And then is to depict the composite behavior, we'll also define the composite stage construction, that is the stage where we consider girders alone, and the stage we consider the slabs being cast. One interesting thing in MIDAS is during the design process, both the checks are performed, that is for constructability, that is before casting, the stability for the girders for lateral torsional buckling is checked, and also after the composite action it is checked. So before going to the next session, I'll just show you a quick demo of how to quickly generate these models using a MIDAS software. Okay, so I'll begin with opening a new file. Okay, so before we proceed further with the wizard, we'll have to define basic material properties and section properties. So I'm just going to properties, material properties, and say add. So with this release of 2.1, we have updated the steel material property database with IRC. So we have also included the structural steel properties, that is E250 according to the steel codes. So I just choose E250 and then say apply. Similarly, I'm going to define a concrete property for the slab. So I just go to IAS and I'm choosing M30 and just say apply. Okay, and cancel and close. So next step, since we are considering the construction stages as well, we'll have to define the time dependent material properties. So I can go to properties, creep and shrinkage, and say add. So in this case, since it's a steel, we are going to consider time dependent properties only for the slab. So I'm just using IRC and 30,000, and I'm just approximately choosing it 1. Later it would be automatically recalculated when we are defining the composite construction stage, and just show. So this is the creep behavior for M30, and just say OK. Similarly, I'll have to define the property for compressive strength. So M30, and this is going to be IRC 112, and this is going to be FCK plus delta F. So this is delta F is 10. I can refer the code table number 6. So this is going to be 30,000 plus 10,000, that is your delta F, and then I'm just going to choose normal cement and say draw. So this is the strength of variation with time, and close. So after that, we'll have to link this material time dependent properties with the material property that we have already defined. So I'm just choosing M30 for creep, M30 for compression strength, and M30 from the material property we defined, and then just say add. So this is important when you're doing construction stage analysis, else the variation with time dependent effect will not be considered. So after this is the section properties. is we'll define the section properties and say add. So again, since it is a steel composite, I am going to define the section property and the steel composite. I'm just giving a name, composite Girder. And here you can choose the type of steel section you want to use, that is steel I, steel tub. So steel box is box, and steel I type 1 is symmetrical slab, and steel I type 2 is unsymmetrical slab, for example near the edge slab, if you want to consider steel type 2. And then these are for the PSE, so I'm just going to use, and if you want to have a gentle section property, you can use composite gentle and import it from SPC. So for this purpose of the webinar, I'm going to use steel I type 1. So BC is your breadth of the slab. This is generally going to be your center distance between the girders. So this is going to be 2.75 in this case. And then thickness of the slab is 0.23 meters. And I'm considering a height, a distance between the slab and the steel girder. I'm using a 0.075 meters. And then HW is nothing but your clear depth of the web, which I'm assuming to be 1.5, and thickness of the web is approximately 11 mm, and then top flange width is 0.36 and bottom flange width is 0.45. And then next is the thickness of the top flange, which is going to be 0.03, and bottom flange 0.04. Okay, after this we define the material properties. This is basically to compute the modular ratio between the steel and concrete to compute the transform section properties. So again, I'm going to choose first as a concrete material for the slab M30, and the next is for steel, which is going to be E20, and say okay. So this will update your modular ratios accordingly, and then we input the offset. This time again it's going to be center top, and let's say okay and say apply. So this adds the composite section property. And then one more property we are going to add is angle, that is for the braces. So I'm going to use user defined database user section and choose the type as angle. And here again I'm going to use the database. I'm going to use ISA 90 cross 90 into 10. Yeah, you can see the parameters getting updated accordingly, and then say okay. So if you already have all these material properties to be imported from some other model, you can always do that. I choose import and choose that particular model, and here again I can choose all the material properties that have been already used. One thing to note is that if the IDs are similar, these would get overwritten by the sections which are going to import, depending upon the options we give here, that is whether to keep ID or to change the ID. Right now I'm going to import all these sections which are previously defined, and then I say okay. So this gets updated. So this helps us to save the repetitive process of defining the section properties again and again. This procedure is also applicable for the material section properties, that is import option again here. So again we can choose the material properties which we want to define from here. Okay, so after this we can right away go to the modeling or modeling of the bridge using the wizard. So for that I'm going to go to structures, and here is the steel composite bridge wizard we are going to concentrate on. So I'm just gonna, so this is the layout of the wizard that we have chose. So if you see, there are 4 options, so 4 tabs, that is the basic layout, and then the section definitions, like what component, what section type is going to be assigned to particular component, and then is the loads that we want to consider. These are some default loads that generally acts in a steel bridge, so you can have all these things, or after the wizard generation we can also manually add certain loads if you want. And then is the construction stage. If you see, These construction stages again, you can see this construction stage description and the load conditions that has been considered, etc. There are also some advanced options for considering the negative moment zone and other things. These generally come into picture for Asher code. And then deck splits construction, like if you want to change the deck activation deactivation depending upon the construction stages, you can also specify them here. So what I'm going to do is I'm going to open a wizard file which you already have the inputs. So I'll just explain all these parameters which are involved. So first is the type of the girder, you can choose the type of the girder, whether to be steel, eye, box or tub. And then is the modeling type, whether you need it to be all frame, all plate or a deckers plate, etc., as I've explained previously. So this is a two span bridge with the first span of 24 meters and the second span is 28 meters. If they are of same span length, then you can simply give as 3 at 15. So this will automatically consider 3 spans at each 15 meters length. If they are unsymmetrical, then you have to input each of these span length separated by a comma. And then is the deck width, which is going to be 11 meters. This is including the footway up on both sides of the roadway, which is 10 meters. And then you can also have skew angles. I have not introduced this. It's a straight bridge, so I'm not introduced any skew angles. And apart from that, there are also some advanced options, like you can introduce skews for each and individual pier. Like if each one pier is skewed with respect to the bridge superstructure, those skew angles could also be separately given. See, you can see here, since there is two spans, it has considered one pier by default and two abutment at each end of the bridge. So you can modify these angles as per the wish. So next is the layout offset. So talking about layout offset, you can refer the guide diagram over here. So if your bridge is offsetted from the center line by particular offset length, then you can use this layout offset which is given here. This basically comes into picture for your convenience in giving the girder positions and etc. So then next is the boundary conditions, and as discussed, I'll also introduce about the curvature that can be given. So we can give the radius for the curvature. You can have a concave type or a convex type, and if you are interested in multi-curve, then you'll have to check on the multi-curve option, go to advanced. So here are the basic options that you'll need to give for the for defining the curve options here. So I'm not going to show this now. And then is the boundary, bearing type and width substructure if you want. So you can just go to the guide and see what are the types of inputs you need to give for creating such modeling. So this time is going to be bearing type, just with a superstructure. And then supports, we can have them as elastic links or direct supports. So and all other options over here. So the deck thickness, which is 0.23, and then material for deck is M30. Girder property is E250, and similarly for the bracings. And then as the transverse deck elements, spacings are given as 2 meters. This is basically to consider for the transverse distribution, basically for creating dummy cross beams across. So the distance for that. And then we'll have to define the bracing details. You can, again coming to basic bracing details, I'll just open the guide diagram. So these are the two types of bracings you can define using MIDAS civil, that is either truss type or a beam. So I'm just using truss since we have cross bracings, and you can choose the bracing parameter sections from here, and then you can also choose the type of bracing you want to use. So this case I'm using X bracing. And then this is again there is top bracing, bottom again I'm using so you can also see the detailed explanation of what these parameters are. Apart from that, the distance between the distance from the bottom of the cord, top of the cord could also be given, and after these you just have to simply add. There are two types of bracing I have defined here, that is type A, and type B is Again a truss brace with a V type of bracing, like only the V and a bottom bracing without the top. For top, I'm using a cross beam element, that is IS 250. So this is the top is going to be a beam, and bottom we are going to have this V brace arrangement. Before going to girder information, we'll have to also specify the number of girders we have given here. So again, there is a guide diagram which is available for us. So this is the number of girders we want to give. We have input here, and then the distance between the girders. So this is basically with respect to the center of the deck. So minus 4.125 in the negative direction, and minus 1.35 in the negative direction, and then 0 is the center, 1.35 and 4.1 in the positive directions. So if my offset is there, then I'll have to consider the offset distance also, keep offset distance also in mind before I give the girder locations. So after 4 girders are given, the input for all the 4 girders are generated. So you can choose the type of girder properties you want to use. You can use the same property along the entire length of the girder, or you can also have different property depending. For example, if it's a tapered section, then you'll have to consider a different section property. So you'll have to specify the start and end distance as and when you want to keep adding the variation in the section. So here you can specify the number of divisions. So this is basically to input the variation. For example, if I'm changing it to 3, then I can input different type of sectional property along the same length of the girder. So again, there is a guideline for that. So generally in case of steel girders, we have variation in the flange thickness. For example, the mid, to have more moment capacity, we increase the flange thickness in the mid, gradually decreases as towards the support. So to consider those variations and all those effects, we can make use of this division option over here. And then there is also options to give the stringer properties. Splicing, if you want, those could also be given. So generally there's an option, if the properties are same for all the girders, you can simply say copy current girder data to all the girder sections, and you can choose the list all and say okay. So all this girder data in the girder 1 will be copied to all other 4 girders, or if you want to change them as well, you can change them individually for the other girders. So and then again different support. So if your support has different basing arrangements, then you can choose them accordingly as per the options available here. And for bracings, again you'll have to define the placements of the bracing along the girder. You can either have it different bracing for the girder, or you can also have a similar bracing distance for the girders. It could be in terms of division distance or divisions per span. So this case I'm using divisions per span, and you can choose the type of bracing which you have already defined, number of divisions, and the angle. Like if it's skewed, you can give an angle. If it's normal, then you can just have a perpendicular direction. So this will complete the section. And the next is the layout. So this comes to the transverse property definition of the bridge. So as you can see, we have options for defining a carriage, the parapet width, and then the carriageway width, that is B2, and the median if required, and then is for the other way. So having these guide diagrams, you can input these parameters. The next is the loads that need to be considered. So if you see, these loads are classified before composite and after composite. So before composite, we have the self-weight wet concrete load that has to be defined. So for wet concrete load, we'll have to give it the density and the thickness. And then in case of formwork is there, you have also options to give the formwork load. You can choose which are the loads you want to consider and not to consider. Then if you're considering for after composite, we have this barrier load, median strip if it's given, additional load if there is any, we can give them. And wearing surfaces are also there to be considered. And then again we have options for moving load cases. You can choose Indian code and then say okay, and the moving load will be taken. And apart from this, we can also have the traffic lanes directly defined from here. We can also directly define the traffic lanes. So from here you have to define the number of lanes you want to give. So in this case I'm going to consider 4 lanes. So this is basically I'm going to consider class A and 70R loading. So as indicated by IRC 6, we'll have to define the lanes. So that leads to that might lead to a large number of lane definitions. So right now I'm just going to choose define 4 lanes. So deriving upon the calculations, these are the lanes I'll have to define. So this is from the edge of the slab. So this is 1.63 D1, and then next is 4.65, and then D3 is 6.4, and the last one is 7.8. So you can refer the code of deriving all these parameters over here, and then say OK. So this will define the traffic lanes, and the next is to define the vehicles. So I'm going to include class A load and 70R. So these are the two vehicles we need to consider for 10-meter width of the roadway. So after this is done, then is the construction stage that we have to provide. So deck pouring sequence is considered, and then in order, if you want to consider negative moment zone, then you have to you can consider. And then is these are the construction stage activation. So we can discuss the activation in detail once we are done with the modeling, so it will be easier for understanding. And next is the reinforcement detail. Since we are performing design, we'll have to input the reinforcement detail also. So I'll just get into the reinforcement detail. So in this case, we'll have to choose the section property, and we can give the reinforcement details like as we want. So an easy way of giving reinforcement is using the multi-add. So here in multi-add, there are two methods of there are various methods of input. I am choosing input method A. So here what I choose is since it is a symmetric section, I am using Y. Y is basically your horizontal axis, and Z is the vertical axis for the section. You can see the dimensions over here. Axis over here. So here I'm choosing reference as Z top. So this will enable us to easily define the location of the bars. So here Y will be 0, and Z I'm giving a cover distance. So say 0.05 meters. Okay, so this would be, that is 50 mm is my cover distance. The number we want to consider, since it is so I can consider say 25 of them, and spacing as 0.1, and then diameter is P12, and then P12. Okay, and if I say OK, you can see the rebars are easily defined. Okay, you can choose a comfortable way. There are various ways you can define the rebars, so you can choose a comfortable way of doing that. And shear reinforcement, this is generally not applicable, because since slab we are not interested in shear reinforcement. So similarly you can do that for girder too. Go to multi-add. I'm going to give the same centroid top. This is going to be top. This is 0 and 0.05. Number is 25. Spacing is 0.1, and then 12 and part 2. Okay, then let's say okay, right. So this is done. So, but in MIDAS civil, for negative moment, we do not consider the slab properties for calculation. Only the reinforcement and the girder properties are considered. We can discuss about that when we get into design part. So this is done, and I just say close. Okay, so we've defined the reinforcement properties. So what you can do is you can also save this wizard, this as a wizard file. For example, I'm saving this again. What this helps is in order, for example, after modeling, if you think that you need some further more modifications in the model, you can simply undo it and reopen this wizard file with all the informations which you already provide here, and keep modifying the model. So this is going to help you for easier modification of the model at the later point. Okay, and I just say okay. So you can see the model is quickly generated. Once you get familiarized with the wizard, it is very easy for modeling these types of bridges. Simple manual method might be easier for straight bridges, but when it comes to curved bridge with so many girders, it is really complex and time consuming. So these wizards will help you quickly generate those aspects as well. So I'll just quickly review the parameters that have been generated using the wizard. So first is the material property. So these dummy materials for cross beams are automatically created even before we have not defined them. And then are the section properties. Again, these two section properties have been created to consider the loading, and cross beams are for consider to be taken into account for moving load cases. And then the construction stages, composite construction stage is also generated. So so here in composite construction stage, we can check at what age and what activation stage these are being activated. So I'll just give update all H. So all the notional values would be computed automatically by performing this operation. And then next is the nodal local axis. This basically comes into picture in case of curved bridge where your bearings are oriented toward the tangent of the bridge. So in that cases, this nodal axis need not be given separately, it is automatically considered. You can also see the various types of load cases that had been generated during this wizard process, and then also the traffic lanes. So these are the traffic lanes that has been created using the as per the definition in the wizard. So so next step is like we'll have to define moving load cases, which could be done after the file is generated. And then is the construction stage. So I'll just go to the hidden view for better understanding. So first stage, the girders along with the bracings are activated. I'll just activate the loads and boundary conditions as well, and the loads. Okay, so these are the boundary conditions that has been developed. So in used a support, so these are not connected with elastic link, and then support. And then is the stage 2 where the wet concrete load is acting, and then stage 3 is the composite action of the slab. You can see the wet concrete load being automatically deactivated. And then stage 3 is the filling between the next stage is filling between these two spans, but concrete load for that particular length of the span, and then again the composite action would now take place. And then stage 3 I mean stage 3 is this is the wet bearing course load and the barrier loads, parapet load, and stage 4 is for long-term effects. So this is so this actually saves us a lot of time defining a group, defining the construction stages, and while considering the lanes generally for a particular girder, these are the three main critical positions we consider. That is the vehicle are running directly on the girder, so this will give you the maximum moment. And for considering the torsional and shear effects, you consider the vehicle being loaded like extreme to the extreme left of the lane and the extreme right of the lane. So these three lane cases will be applicable for any particular vehicle. So considering these, we have to define as many number of lanes, and while forming the load combinations, we'll have to consider these considering the simultaneous loading of these vehicles on corresponding lanes. And regarding the flow of traffic, both the direction is possible. Moving forward and backward, both the directions are considered to consider the maximum effect that would cause on the girders. And then we'll give the load combinations, and then we'll also have a look on the post-processing capabilities of the software. And I'll quickly open one of the traffic lanes. So you can also see the crossbeam action is also taken place directly. So the span length is basically considered for considering your impact factor. So either you can manually input the impact factor or directly given the span length. So the software automatically considers the span length for taking into picture of the impact factor. So next is we'll have to define the moving load cases. So I just go to load, moving load, and moving load cases. Say add. So here first is class A. I'm just considering class A type of loading. I'm unchecking auto load combination and I'm going to give that manually. So minimum I'm going to consider 3 lanes for class A. So I just change the vehicle type as class A and consider. You'll have to double click to select them or and say apply. So this will consider 3 lanes with class A and say apply. And similarly for class A plus 70R 70R again I'm going to define so for this class A again I'm going to remove these 2 lanes because with 70R we cannot load the adjacent, so I'm just applying apply, and then for 70R I'm choosing this lane and say apply. Okay, so this will consider combination of both class A and 70R and just say okay. Yeah, after this is done, we have completed most of our modeling process. Some basic analysis control that we'll have to look into is the moving load analysis control. So here you make sure you check in normal plus concurrent forces and combined stress forces, combined stress calculation. So in case of plate elements, if you check stress calculation only, then you will be able to see stress results, and only if you choose normal plus concurrent forces you will be able to see results of concurrent forces. So you can choose the type of bridge as steel because the impact factor calculation depends upon the type of bridge you choose here, and then say okay. And under construction stage, since it is a composite bridge, make sure you activate this option of calculating output for each part of construction stage. So basically what happens is the individual forces that is acting on the girder and the slab are separately displayed, which is important for the construction stage analysis. Apart from this, we also have the erection loads that has been added. So these erection loads are basically those loads that you want to differentiate from the dead load while you are viewing in the construction stage. That is, load cases to be distinguished from dead load for CS output. Then we'll have to add the erection load. That is also done automatically. And then is the load cases. So if you see the load cases, these loads are all categorized under construction stage load, so that during the load combinations they do not repeat themselves. So next is I'm going to analyze this results load combination, and I have to define the combination under steel design. So first I'm going to define moving load. So here I'm choosing inactive because I do not want the load combination to be considered for design. So here I'm going to consider 2 load cases. I'm going to consider envelope type, that is envelope of class A and class A plus 70R. Okay, and then next is the serviceability condition. Here I'm going to categorize it under serviceability, and I'm going to choose all these loads: dead load, erection load, 2, 3, like and then tendon primary and tendon secondary, and then creep secondary, and then shrinkage secondary, and this combination of moving loads. Okay, and then for strength, I'm going to categorize this under strength, and here again dead load just 1.35. okay, and next is the wearing course. I'm going to use 1.75, and then for the parapet again I'm going to use 1.35, and then next is tendon primary, and then tendon secondary, and then creep secondary, shrinkage secondary, and for live load I'm considering 1.5. okay, just need to make one modification with service. Service here, tendon secondary and primary is 0.9 as per code, so I'll just make that. Okay, so this will complete the load definition, and as I say close. So this will complete, so we can just next step is to run the analysis. So I'm just going to run the analysis. Okay, the analysis is complete. So we'll just quickly look into the results. So for results, I go to results for the reactions. Say apply. So here we can just see. Going to look into the other view. So this will give you the reactions that is happening, and then after reactions, if you're interested in deformation, you can go to deform shape and choose the corresponding components, and then they say apply. Okay, I'm just checking off the value. So negative m minimum is considered under m minimum case, and m all is the envelope of all the cases. Okay, and then next is the forces, beam forces. If you're interested in, again you can choose the required component and then just say apply. So this will give you the bending moment forces. There is also a legend view to look into. Okay, and then next is for moving loads, we have moving load tracers. So basically this is going to help you find out the location of the vehicle which is going to cause maximum forces for a particular element. For example, say if my element of interest is 150, I choose that and the corresponding component, and then say apply. So this will give you the position of the vehicle that is going to give the maximum moment on that particular member. Also, there is one option to convert these vehicle position into static load. What I have to do is I go to and say OK. Say write minimum maximum load to file and say OK. So this will basically convert all the loads into a MCT command shell file. Okay, so these are the converted loads that has been considered as static load. So what I have to do is you have to copy these and then go to tools, MCT command shell, and then paste them and say run. So this will again delete your analysis results. So you'll have to run the analysis. So right now I'm not doing that. Say cancel. No one can close. Okay. So after this is done, if you want all these results to be in tabular format, you can also go to results table, and then you have for reactions. You can choose the load cases for which you are interested in and the element numbers to be given here. I'm just choosing one right now and say OK. So these are the reactions that comes for the moving load cases. So in moving load cases, you do not have a reaction because these are not concurrent. These are not concurrent forces. These are the maximum forces. So you do not get a summation of all these things. And then for beams, again the same procedure. Go to forces. Choose the element of interest and the components and the parts, then say OK. So these will be listed here. Okay, and then if you're interested, you can also define concurrent groups, that is going to moving load and say concurrent reaction group. So you'll have to form a group, for example say substructure, where you generally have the reactions, and say OK. I'm not going to do that right now and just show the procedure. So once you do that, you'll be able to extract the concurrent reactions that is happening at the bearing position. So basically this is going to help you to get the results for your bearing design. Okay, so these are some of the post-processing options that is available. Let's just continue forward with the design. So I have to go to the design tab, and under composite design we'll have to choose IRC code IRC 22/2008. So we'll just see what are the basic parameters we'll have to set up before we can perform the design. Under common parameters, first is a frame definition. So this is generally not relevant for superstructure. This would come in place when you are considering substructure. So I'm just putting it as unbraced sway or non-sway because effective length factors are not coming into picture now, since it is just a beam design. And then next is member assignment. So under member assignment, since I'll just before proceeding further, I'll just activate the trim in O2, yeah, and the girder sections. I'm just considering one span of the girder, let's say. So here if you see, these individual girders are segmented into individual elements. So for design purpose, what happens is the length of this particular element is considered, so that is going to make difference when you're calculating the lateral torsional buckling effects. So we'll have to assign all these elements as and define them as a single element, so the entire length, span length, is considered for a calculation of lateral torsional buckling. So I'm going to choose automatic, and I just select all of them and then say apply. So automatically, depending upon the continuity of the elements, the member assignment is taking place. One thing to note is member assignment is possible only for elements of similar section properties, same section properties. So if it has a different section properties, then you cannot give the member assignment. Okay, so back to the design tab, and then is reverse local axis. This is in case we want to reverse the member axis. And unbrace length and brace length, again, if you want to give them manually, you could input them from here. Effective length factor, and so these are the basic two modifications you need to make. So now getting into the composite design parameters. So first is the design parameter that we'll have to change. Considering the design code, so these are the basic parameters these are the partial safety factors that are considered as per the codal provision. So stress limitation those are also given. These could also be edited for the checking purpose. And then coming to the limit states and serviceability limit states, these are the checks which are available, that is bending resistance, vertical shear, lateral torsional buckling both for construction stage and after construction stage, and then transverse force, longitudinal shear, and fatigue assessment is also there, along with stress limitations and a longitudinal shear check. This is longitudinal shear check is nothing but for your shear starts. Okay, and next is the design material. So design material, again, we have just defined we have already defined for the structural steel, so we'll just have to also include the concrete material for slab, and the reinforcement material for the rebars. So I'm just putting FE415 and 415 and say modify. Let's close it. And then next is longitudinal reinforcement. Longitudinal reinforcement is already we have given, so we can just proceed forward with the next step. First I'll have to define position. I'm just selecting all of them and I say apply. So these are the selected members would be basically design, and then is a position for design output. So as I've already instructed that a detailed Excel sheet is generated for each individual elements. So which are the elements you want to design or you want to generate the Excel sheet, that is given for position for design output. So I just select one element, because if I'm going to select all of them it might take a little time. So for the demonstration purpose I'm just selecting this one particular element and then say apply. You can also include these elements from the table here. So this table and the end and j end could be modified from here. You can also use both the ends, so I and j, let me assume. Okay, and then next is shear connectors. So here you'll have to give in the details of the shear connectors. For example, this is going to be the number of connectors in a particular row. So for all the details on these parameters, you can always refer the help menu by clicking on this icon over here. And so for example, I'm just giving 3 connectors, and then tensile strength of the strength. This you can refer the code and you can input them accordingly. So I'm considering 400. Tensile strength is the ultimate strength that you need to consider, and the diameter of the shear, let's say 225. Again, you'll have to refer the code, a relevant code, to input all these parameters. And this is 0.075, and center to center, or in the transverse direction, what is the center distance you are considering? That is along the row, along the transverse direction of the section, not along the length. And then this is the spacing, that is lateral direction or longitudinal direction. Again, I'm considering as 0.1 meters. I'll select them all and then they say apply. Okay, so this will complete the shear reinforcement definition. And then transverse stiffness. So one stiffener is basically stiffener present at only one side of the web. Two stiffeners means both the side of the web the stiffeners are considered. So height of the stiffeners basically will be the height as 1.5. and thickness I'm assuming point say 20 thick. And then pitch of the stiffness is the distance between the what I'm going to do here is query node. I'm going to find the distance between these two elements and I'm going to give them. So it is 2 meters. So I'm going to give a pitch of 2 meters. And then you can also include intermediate rigid stiffness. This so intermediate rigid stiffness I'm also giving 2 meters. And if there is non-rigid stiffness, that also could be given. So what is the difference between rigid and non-rigid is, if you're assuming a stiffener to be rigid, then the effective length taken for your lateral torsional buckling would be the distance between the two rigid stiffeners. If it is a non-rigid stiffener, then the presence of that is ignored for calculating a lateral torsional buckling, and the entire span length is taken into account. So that is the thing. So right now I'm just giving these properties and I just say apply. Okay, again sorry, I'll have to select these elements and I just say apply. Okay, so next definition is stiffness properties are given, and then again we have to reiterate what are the support nodes. What are the support nodes for which the rigid end post should be given. So what you can do is you can just display. So I'll just activate the supports here. So these are the support nodes basically. Okay, so these are the support nodes. So we'll have to specify the end rigid. This becomes important again. I have mentioned for the post buckling strength of the web. So here node 6, 8 and 10. Okay, and I just say add. So these are the rigid end post. Okay, and then next is lateral torsional buckling data for plate girders. This option will have to check if you want to consider the lateral torsional buckling effect into picture. So I have to check on the fatigue factors. So this is going to give you a fatigue assessment, that is whether the fatigue strength you are considering is sufficient or not. Basically this is just an assessment, since we are not doing fatigue analysis over here to compare whether it is passing or failing. What it will give you is just the strength, like what is the fatigue strength for the given strength you are considered. And then next is the serviceability load combinations. So this is again you'll have to categorize them depending upon putting in the characteristics and then just say okay. So this is basically going to be taken for your serviceability parameters. So these are the basic design parameters that needs to be defined, and apart from that we'll also have to give the span data. So here under steel composite you have span information. Okay, so here you will have to give the span data. So now what I'm going to do is I'm going to select these girders. I'm going to select the girder span 1 and just say add. Okay, so if there is a support, then the support end are automatically considered. So if you want to consider a different spacing, for example if you do not have rigid stiffness but you have cross beams in between, in that case also the effective length for lateral torsional buckling gets reduced. So in that case what you can do is at the spacing of positioning of the cross beams you can specify a support conditions. So the distance between these support conditions are going to be considered for your calculation of the lateral torsional buckling. Okay, so this completes a span definition. So now we can directly go forward, proceed with the design. This indicates that the design is complete. So next let's just quickly produce the result. New file and save as. So here I'm going to save this as steel composite report. Okay. Okay, so this is the detailed report that is generated. So I'll just review this quickly. So the design parameters which has been considered, you can also see the clauses are also mentioned for the convenience of checking. The material information, depict a representation diagram, all the section properties that has been calculated, and then stiffness, section stiffnesses before cracking, before composite, after composite and cracking. So check. And so the bending resistance in positive directions, you can also see the stresses that are coming on the flanges. And first is the classification of the sections. So each of individual components, that is top flange, web and bottom flange, are classified, and then the class of the section is decided. And then minimum web thickness is also checked. Minimum web thickness criteria is also checked. So this is basically depending upon the requirements of the steel code, that is IRC 24. And then the plastic moment is capacity is computed. So this is a very complete report considering all aspects that need to be used. Okay, so along with this, we have also developed a design guide to help you understand the design parameters and other things involved in the design. So introduction, these are the basic design criteria that we check, that is the cross-section proportions check, the bending strength check, serviceability check, constructability and fatigue limit state. So classifications, what are the criteria adopted for classifying the section, and then when does a particular section fall into class 1, class 2 and class 3, and how are the stiffness and steel stiffness considered section classification. And these are basically the parameter, the section properties used. So as I've already mentioned, so these are the three stages which are considered: steel only, non-composite, that is considering the sulfate alone, and composite considering the integral activity of both. And then time dependent effects, the modular ratio is also taken into picture according to IRC 22 recommendations. So these are the design parameters, that is the partial safety factors, and the compression stress, what are the compression design compression forces considered. So again, these are the material properties as per material properties of the structural steel we have considered. For example, if you are considering E25, then if it is if the plate thickness is less than 20, then we consider a yield stress of 250. If it is greater than 40, then we consider a reduced yield stiffness of 230. So all of these parameters are considered within the software itself. So this is the design parameter dialog box, and then the material design strength of the material, which I have already explained. All of them are explained in detail in the design guide. So these are the moment, position and the component of flanges which will contribute. Classification of cross section, and there is also a special as per the code. So if a particular flange section falls in class 1 and a web flange falls in class 3, then an equivalent web section is also considered. So all these are also considered into picture, and these are the moment calculations. How are the moment calculated? So this is basically this is for the plastic moment calculation, considering the force balance. So depending upon the neutral axis position within the web, within the slab or within the web, these are the calculations, moment calculations which are considered. So this could be used for your verification purpose. And then how the elastic bending capacity is calculated, and these are some inputs for your stiffener properties. And similarly the bending check, and then how the lateral torsional buckling is calculated, and then combined effect of bending and axial compression is also taken. So this would complete, so this is the report. So this will complete the strength bending moment check. And then coming to strength parameter for shear, again we calculate, we check for the plastic shear resistance, also the shear buckling. If there is buckling, then reduced shear is also considered. For example, even there is reduction in plastic moment when there is high shear condition. For reduction in bending moment capacity is also considered. This is basically for buckling resistance, that is if you want to consider the post buckling strength of the web, that is also considered. Again I will explain the transverse stiffness and the end post. Similarly interaction between bending and vertical shear. So if there is a shear of 0.6, if the design shear is 0.6 times greater than the plastic shear capacity of the section, then a reduced bending moment of the section has to be considered. So those computations are also taking place. And then is resistance to longitudinal shear. So this is basically depending upon the shear connector data you provide, the longitudinal shear that could be resisted is computed. So this comes in terms of the spacing of the shear connectors, with sufficiency in spacing of the shear connectors. Full shear connection check is considered. Okay, so this is for longitudinal shear. And then is the fatigue assessment. So you'll have to refer the code to input the fatigue parameters, and the software will give you will compute the strength, what is the fatigue strength for the given parameters. Okay, and then so this will complete your strength checks. And then is the serviceability checks. So again, serviceability checks, if you see, normal stress for the girder alone is checked, and also for the shear stress, permissible shear stress. Then is the combined, which is combined shear and normal stress is also taken into picture. And then as for the concrete slab alone, it is taken, and also for the reinforcement slab. Apart from this, we also have check for deflection, fatigue check for shear connector, serviceability load cases is also considered. And then is the deflection control. So all these are considered in the detailed report. So this design will also help you for the verification purpose. So as I've explained, so these are the list of design check which is available: strength check, serviceability check, fatigue check, constructability, shear connectors, and longitudinal stiffness. So this is the design report, that is a tabular format, giving you an overall view of the pausing and failing members, and a graphical format is available along with the Excel report. Some more tips on designing the steel members, how to consider certain design aspects while in come to modeling. For example, it is common in steel girders that you have holes in the web, basically for service accessibility reasons. You'll have to provide holes in the webs. You can give scale factors to the web to consider the reduction in stiffness property, and for analysis purpose to consider the stress distribution accordingly. Only that part of the section you can design it as plate elements, and the end of the plate, the end nodes of the plate are connected with these line element beam models with rigid links. So this will ensure the continuity of the member, and also you will get the stress distribution accordingly depending upon the hole proficiency. And then diagonal expansion joint. So again, this is generally comes into picture with steel design, composite girder, for example. So since the composite action have to be considered, you'll also have temperature additional stresses developing due to the continuation of the slab. So in those cases where you'll have to provide the expansion joints, we can consider it this way. So basically these are the two slabs which is resting on the single girder. So while connecting them with the elastic links, so one end of the slab could be connected with the rigid elastic link, and the other end of the slab we can have compression only links being connected. So what this implies is it will not transfer forces, transfer moment and shear forces, but only the vertical load, that is only the dead load transfer would happen. By this way we can ensure that diagonal expansion joint could be molded. These are some modeling tips that might be required during the process of modeling for a steel composite. So this completes the webinar. So if you have any queries, please write to us at techsupport@midasit.com. Thank you.